module 1 will have some introduction. Okay, because based on this introduction, the rest of the module is depending. Okay, at least the first topic of the module is depending. So that's the reason, like, let us go with the very basics. Okay, so so what is an atom? What is an atom? See, I want answers from you people. I'm not going to answer those questions because what is atom? All this you might be studying from your 6th standard or 7th standard, right? Yes or no, ma? And yes? Okay, so what does an atom contain? What does an atom contain?
Small particles.
Particles.
Protons, neutrons, electrons, right?
Electrons.
Okay. So protons are said to be positively charged, and neutrons are neutral, and electrons are said to be negatively charged. Okay, so all the electrons will surround your nucleus. Okay, nucleus is a part, is a center part where your protons and neutrons together are present. Okay, so electrons are revolving around the nucleus, right? Yes or no, ma? So these are nothing but the electrons, whatever, like with some circles, darkened circles I'm representing, those are nothing but the electrons. Okay, so these electrons are revolving around the nucleus. Okay, so atomic weight, atomic weight, atomic weight. What is atomic weight? Atomic number. See, whatever our discussions, whatever we are discussing, these all are useful for us for our analysis in the next diodes and all. To understand them clearly, we need to know all this. Okay, that's the reason, like, I am asking you all the very basic questions. Okay, let me not ask you the questions, I will only answer you. So atomic weight, because it will eat my time. Okay, and moreover, you people won't even unmute yourself. Okay, it will eat my time. So let me just give the basics. Okay, you can just recall them. Okay, so atomic weight is nothing but number of protons plus the number of electrons in an atom is given by the atomic weight. Atomic number is nothing but either it can be either number of protons or the number of electrons of a neutral atom. Okay, when do you say that the atom is neutral? If the number of electrons and the number of protons are same. Okay, then we call them we call that particular atom as neutral. Okay, so again, if the number of protons and the number of protons are equal, then we call them that particular atom is neutral. Okay, so what is when do we call whether it is positively charged or negatively charged, or positive ion and negative ion? Positive ion, when we call it as positive ion, we call it as positive ion when an atom loses an electron. Loses an electron. Okay, when an atom loses an electron, it will become positively charged, or it is said to be positive ion. Okay, negative ion, coming to the negative ion. Okay, so what happens here? Positive ion, in the sense, number of electrons will be less than the number of protons. Okay, so the number of protons are more. Protons are said to be positively charged and electrons are said to be negatively charged. The number of protons are more than the number of electrons, it is positive ion. Here what happens? The number of electrons will be greater than the number of protons. Okay, so gaining an additional electron. Okay, so that is the reason it is said to be the negative ion or negatively charged atom. Okay, so coming to the valence electrons. Valence electrons are nothing but the electrons which are present in the outermost shell. Okay, if you just take silicon, okay, I'll be generally interested with silicon and germanium. okay, silicon and germanium, because our diodes are mainly manufactured with this. Okay, why? I'll explain you. You also know, most of you know, I don't know how many of you know, but most of you know. Okay, so valence electrons are nothing but the electrons which are present in the outermost shell. Okay, so I randomly I have just taken some electrons. I don't even know what is the count. Okay, but it is not like this. The electrons which are to be present in each shell, okay, each orbit or each shell is having a specified number. Okay, so if you take based on spdf KLMN levels. Okay, KLMN are the levels and SPDF are the subshells. Okay, so here you need to represent how the SI atom is there in the like how it is what do you call, how the electrons in the SI is placed. Okay, so that is what you need to know. Okay, so SI, what is the atomic number of SI? It is 14. Okay, so I'll have 14 protons and neutrons, and I'll have 14 electrons present. So the number of electrons that will be present in each orbit is 284. Okay, 284. So 2 will be in the first orbit, 8 will be in the second orbit, and 4 will be in the last orbit. Okay, so this orbit is said to be the outermost shell is said to be the valence shell, and the electrons present in this valence shell is said to be the valence electrons. Okay, so what happens when this atom gains some energy? Okay, what happens, this the atoms which are present may leave the orbit and it may become free. Okay, all this free electrons will move will be in the position to conduct with other atoms. Okay, so that is the reason your energy diagram will consist of valence band, conduction band, and the difference between this valence band and the conduction band is given by band gap or forbidden gap, or we can even call it as energy gap. Okay, so what happens, the electrons will move from the valence band to the conduction band when they become free. Okay, so based on this energy band diagram, based on this energy band diagram, the atoms are divided into three types. Okay, they are conductors. Okay, based on this energy band diagram, okay, where it consists of valence band and the conduction band, based on this the elements or the materials are divided into three different types: conductors, insulators, and the last one is semiconductors. So as the name implies, conductors, in the sense there will be more number of free electrons which are easily moved to the conduction band. Okay, so here what happens is the conduction band and the conduction band and the valence band will overlap. Okay, so overlap. Okay, because it is overlapping, there are more number of free electrons present. Because of more number of free electrons, it can easily conduct. That is the reason the name conductors. Okay, when it comes to the insulators, the band gap will be more. Okay, so the difference between the valence band and the conduction band, the band gap will be more. Okay, so then they cannot be easily there are no free electrons to conduct. Okay, so these are not able to conduct even when you 1 second, ma, 1 second. I'm sorry for this interruption in between. I have got one small work to do. Let me leave this group and I'll join back in 1 minute. Okay, I'll join back in 1 minute. Please don't leave the group. Okay, thank you. Please wait here.
Shared your
Hi, baby.
Okay, I'm sorry for the inconvenience. So let me just continue. Okay, so insulators. So the band gap will be very high, and like it means that there are no free electrons to conduct. Okay, so that is the reason they are said to be the insulators. Coming to the semiconductors, they are neither conductors nor nor insulators. Okay, it means that it has an ability to conduct when an additional electrical field is given. Okay, so these semiconductors are these semiconductors are said to be a good insulator, or it can be the conductor. Okay, so it will act as an insulator in its purest form. Purest form in the sense, see, if you see the silicon, okay, silicon is a semiconductor device. So to fill its valence shell, it needs 4 more electrons. So what it will do, this silicon will share its valence electrons with the other similar kind of silicon atoms. Okay, so here covalent bonds are forming. Okay, so the silicon in the purest form is said to be a good insulator. Conductor, by adding some additional atoms. Okay, like I'll show you which kind of atoms to be added and all. Okay, by adding some additional atoms, we can make them work as an insulator, work as conductor. Okay, insulator in its purest form. To make it conduct, we have to add some additional impurities to it. Okay, so that is what your semiconductor. So here whatever we will be studying in our further discussion, will be studying the semiconductor devices itself. Okay, semiconductor devices. Okay, so so here I'm telling you that we are adding some impurities to the semiconductor material so that it will convert to the conductors. Okay, so here you can add two types of impurities. Okay, one is said to be the trivalent impurity, or or tetravalent impurity. Okay, adding something is said to be the doping. Okay, so adding something to the pure semiconductor atoms is said to be the doping. So here what you need to do, you need to dope the semiconductor atoms with an additional atoms. Okay, so that it forms two different types of semiconductors. Okay, so I mean to say that semiconductors are classified into two types: intrinsic semiconductors, and the other one is extrinsic semiconductors. Intrinsic semiconductors are nothing but the pure semiconductors which are forming covalent bond. Okay, so I'm not interested with intrinsic semiconductors much. And coming to the extrinsic semiconductors, I'll be doping an additional atoms to this silicon atoms, so that it will form two types of materials. One is said to be the p-type material or p-type semiconductor, or n-type semiconductor. So p-type semiconductor, I'll be adding trivalent impurities. Trivalent. Well, anybody can tell me what do you mean by trivalent?
The electron which has three valencies.
Electrons. The atoms present in the number of electrons present in an atom in the outermost shell will be only 3. Okay, some of the examples are like boron, indium, like that. You have so many. So all these atoms will have 3 valence electrons. Okay, so these three valence electrons, this trivalent atoms are added to the pure semiconductor impurity. So that time what happens, as I've already mentioned, the outermost shell of the silicon consists of 4 valence electrons. So in order to fill the 4 electrons, it needs 4 more electrons. Okay, but what we are doing, we are adding an impurity, trivalent impurity, whose outermost shell consists of only 3 atoms. So what happens? These 3 atoms. Let me consider. I'm just adding boron atoms. So what happens here? One second. Okay, so what happens here? The 3 outermost shell valence electrons of boron will form covalent bond with 3 of it, but it needs one more atom. One more electron. Okay, so this electron, it can accept this electron. This when you are adding trivalent impurity to the silicon, it is forming the covalent bond, but still it can accept one more electron at this location. Okay, so this is said to be the hole. Hole is like, it is a place where it has the capability to accept an electron. Okay, so here since it will accept the hole, in the sense like here if you observe, it need one more electron to fulfill the outermost shell. Okay, so but that one more electron it can take. Okay, so here I have holes, more number of holes are present. It is said to be the p-type material. P indicates positive. Positive in the sense you can just assume that these holes are considered to be the positively charged. Okay, so this p-type semiconductor material, it is having more number of holes. Okay, so this is a p-type semiconductor material. When it comes to the n-type, here we'll be adding pentavalent impurities. pentavalent impurity in the sense the outermost shell will have 5 valence electrons. Okay, so some of the examples are like arsenic, phosphorus, like that you have some phosphorus. Okay, so all these atoms have 5 valence electrons in the outermost shell. So what happens here, when you add this trivalent impurity to the silicon atom, what happens? See, it has got the boron has got 5 valence electrons. So what will happen? The 4 valence electrons of the arsenic, it will it will form covalent bonds with the silicon, but one will be left free. Okay, so here you can see this this can donate an electron. Okay, so this can donate an electron. So this is said to be the donor atom. Or and if you just check here, more number of free electrons are available. See, in the p type I have more number of holes present. In the n type I have more number of free electrons, which can be easily donated or which can easily participate in the conduction. Okay, so that is the reason it is said to be the n-type n-type semiconductor. Okay, p-type is said to be the acceptor as it accepts electrons, because I have some places empty where I can accommodate the electrons. So p-type materials are said to be the acceptor atoms, and n-type materials are said to be the donor n-type materials are donor elements, because what happens here, I'll have more number of electrons, free electrons present. This can be easily donated, and this electrons will participate in the conduction. Okay, so this is how the p-type material and the n-type material are forming. And if you just talk about your p-type, I can say that the majority charge carriers are see here, in the p-type I have told that there are some holes present. Because of this holes, what will happen, it will accept the electrons to that location. Okay, so more the number of trivalent atoms you add, the more number of holes will be present. Okay, so holes are said to be the majority charge carriers in p-type material. Holes are said to be the majority charge carriers in p-type material. And still, see, because of the thermal excitation, there may be some minority charge carriers present. Minority charge carriers in the sense, very few charge carriers will be available. Those are nothing but your electrons, and these electrons are free maybe due to the thermal energy. Okay, so in p-type, majority charge carriers are holes and the minority charge carriers are electrons. The number of holes present will be very much greater than the number of electrons present in the p-type material. Okay, so that is the reason majority charge carriers in p-type material are holes and the minority charge carriers are electrons. In the same way, when it comes to the n-type material, majority charge carriers, see here, as I mentioned, the more number of pentavalent atoms you add to the silicon, the more number of electrons, free electrons will be present. So if you just check here, more number of electrons are present in the n-type material. So majority charge carriers are electrons here, and minority charge carriers are holes. Okay, in p-type, majority charge carriers are holes and minority charge carriers are electrons. In the n-type, majority charge carriers are electrons and minority charge carriers are holes. Okay, so this is what your n-type material and the p-type material, or n-type semiconductor and the p-type semiconductor. So these are the most important things that you need to note down. Okay, so based on this only, the entire discussion of arts will go on. Okay, hope this is clear to all of you, and all these are like not at all new to you. You all know very well. Okay, that's what I'm saying. You people would have studied from 6th standard. Okay, shall I go to the next part? Anybody has got any doubts here?
No, ma'am.
Okay, fine. So let me go to the next actual discussion. So I have got p-type material and n-type material. This is my p-type material. This is my p-type material or p-type semiconductor, and this is my n-type semiconductor. So as I mentioned, in p-type, the majority charge carriers are holes. Holes generally I'll represent with a circle. Okay, and where when it comes to the n-type, the majority charge carriers are electrons. Okay, so let me just indicate with electrons. Electrons are indicated with dots. Okay, so here this is my p-type material and this is my n-type material. So what I need to do, I need to form in a p-n junction diode. Okay, p-n junction diode, p-n junction diode. Okay, so p-n junction diode, in the sense I need to bring the p-type material and the n-type material n-type material together. Okay, so what I did, I have bought p-type material and the n-type material together, so that what happens here, let me just draw this. So what happens here is, when I bought p-type material and the n-type material together, what happens, this is nothing but the junction in the sense at the place where both are bought together. Okay, so what happens, the electrons which are present near this junction will try to diffuse to the p-type. This is p and this is n. So the electrons which are present towards the n side, it will try to diffuse towards the p side. Okay, so or in other way, the holes which are present here, say generally we'll call holes as positively charged and electrons as negatively charged. Okay, so this holes, see, electrons are moving from here to here, it means that the hole will be formed here. So in the same way, when electron is moving from this side to this side, there will be a hole formed, or I can say that holes are moved from this side to this side. Anyway is fine. Okay, so here what is happening, the electrons which are present at the junction is getting diffused from the n side to the p side. Okay, so what happens here, here the towards the n side, it is losing an electron. Okay, whenever it loses an electron, which ion will be formed there? Which ion will be formed there? See, I have more number of electrons here. Okay, so let me consider that I have electrons in this way, and towards the p side I have holes. Okay, now what I'm saying, when I'm bringing this p-type material and the n-type material together, what happens is the electrons which are present towards the n side, it will try to diffuse towards the p side. It means that the electrons which are present at this junction will tend to move towards this side. Okay, so when it moves from here to here, this side atom is losing an electron, right? So since it is losing an electron, which ion will be formed? Positive ion or negative ion? That is what my question is.
Positive.
Positive ion. Okay, so towards inside, I'll have positive ion formed. Whereas here what is happening? The p side, it is taking an electron, so it is forming a negative ion. Okay, so this diffusion will happen until the electrons will not be allowed to move from n side to the p side. Okay, until then this this diffusion will happen. Okay, once this diffusion has happened, what happens, this further movement of this electrons from n side to the p side will be completely avoided. It means that these electrons will not move from n side to the p side. So this region will act as a barrier. Okay, barrier for the other electrons to move from n side to p side. Okay, and here this region is said to be the depletion region. Depletion region. Okay, this is the depletion region, and this depletion region will act as a barrier, and it will not allow the electrons to move from n side to the p side. Okay, so this is acting as a barrier. Okay, and if you observe, towards the left hand side I have negative ions, and towards the right hand side I have the positive ions. Okay, so there will be the force exerted between this ions. Okay, so because of that, what happens? There will be the, okay, let me write this depletion region up, depletion region up. Here I'll write from here to here, whatever is formed is the depletion region. And see, because of the force exerted here, what happens? There will be the barrier potential present. Towards here, I'll have the negative barrier, and towards this side, I'll have the positive barrier. Both will be of equal strength. Okay, so this voltage, whatever is forming, is said to be the barrier voltage. Barrier voltage. This is your P side, this is your N side. Now I'll have the depletion region formed because of the ions present in the near to the junction. This is nothing but the junction where the depletion region is formed. Okay, so this at this junction I'll have the barrier voltage present, which will be of equal strength on both the sides. Okay, so this is how the PN junction is formed. Any doubts here? Any doubts here? You can ask me.
No, ma'am.
Okay, then now we'll go to the until here whatever I have discussed, it is all basics. Okay, now I'm going to module 1. Okay, so module 1, the first thing is PN junction diode. That's what PN junction diode I have explained you how it will be formed. Okay, so PN junction. So this is my P side and this is my N side, and here I have the depletion region present. And I will also have the barrier voltage there. Okay, so for this PN junction, I'll have 2 leads. This is the first lead and this is the second lead. Okay, these leads are used to see, now the PN junction is formed. So will it conduct? Will there be any electron movement from N side to P side or P side to N side? No, right? Yes or no, ma? See, now after the depletion region is formed, will there be any electron movement from N side to P side, or any whole movement from P side to N side? No, right? No, right? So now what I have to do, in order to make this conduct, I need to provide an additional voltage to it. Okay, so that is what we are going to study in this PN junction diode. Okay, so the one which is connected to the P is said to be anode, and the one which is connected to N is said to be, these are nothing but the leads in the sense like connecting wires kind. Okay, so this is your anode and this is your cathode. Okay, and the symbol for the same is given as symbol for your symbol of your PN junction diode is given as see, if I put a bubble here, it is inverter. So don't get confused with this, because most of the people have done a mistake here. So I'm just repeating. Okay, so this is the symbol. Okay, let me just draw it again. This is the symbol for your PN junction diode, and these are the leads. Okay, so this is your anode and this is your cathode. Okay, this side it is anode and this side it is cathode. Okay, so anode is connected to the p-type material, so this is your P and this is your N. Okay, so this is the symbol of your PN junction diode. How it works, I'll explain you, don't worry, but let me make you clear with the terminology. Okay, terminology. This is your anode and this is your cathode. And if you observe, the the symbol is represents an arrow direction. Okay, arrow. Okay, so this arrow indicates the current flow will be always in this direction. Okay, so the current flow will be in this direction. Okay, so that is the reason here the symbol is in this way. This arrow indicates that the current direction is from anode to cathode. This is how the current will flow through the device from here to here. Okay, so from cathode to anode it will be very less current flows. Okay, so the current due to the majority charge carriers will be given in this direction only. That is the reason you can even correlate the symbol with the current direction as well. Okay, so this is the symbol. Okay, this is a symbol and this is the current direction. Okay, so how we are going to get this current direction, we'll see. Okay, so this is and generally anode is considered to be positive and the cathode is considered to be negative. This also I'll show you. Okay, so now coming to the conduction. Okay, so what I need to do, see conduction in the sense, see I have got the PN junction diode formed. Okay, so this is my PN junction diode formed. Now what I need to do, I see if it is just like this, it will not conduct. Okay, so what I need to do, I need to provide an additional electric field so that the conduction will happen. Conduction in the sense electrons will flow, and because of which the current will be developed. That is what the conduction is. Okay, so here I need to make this PN junction conduct. So in order to make a PN junction conduct, I can connect in two different ways. Let me first take the first way. I'll draw the both the like using the symbol also I'll draw, and using this structure also I'll draw. This is my P and this is my N. Okay, so now what I need to do, I need to bias it. See, providing an additional electric field is said to be biasing. Okay, biasing. So this biasing, this is known as biasing. So I need to provide an additional electric field so that this diode will conduct. Okay, so I have two different ways of giving the connections. One is like P, I can connect to electric field. You will have the positive potential and the this is positive and this is negative, right? So what I can do, I have to provide an additional power supply to this. This is how you represent the battery, right? So I need to connect a battery here. So I can connect this in two different ways. Okay, the first way is P can be connected to the positive terminal and N can be connected to the negative terminal. Okay, so this is the first connection. So where I'm connecting, let me name this as VF. Okay, so P is connected to the positive terminal and N is connected to the negative terminal. So in this case, what will happen? Let us analyze. Okay, so let me draw the diagram properly so that you'll be able to analyze exactly how the electrons and holes are moving. So I have the barrier here. Okay, barrier here. So towards this side I have holes, and towards this side I have electrons. And P and N are equally doped. Okay, now what I have done, and here it will have the negative ions towards left side and positive ions towards right side, right? So this is nothing but barrier. See, whatever lines I have shown here, this is nothing but the depletion region. Okay, so now what I'm doing, I'm providing the additional electric field. I'm connecting a battery. Okay, so if you observe the battery, this is connected, positive terminal is connected to P type and the negative terminal is connected to N type. So what happens here, initially what happens here, if you observe, these are nothing but the holes and these are nothing but the electrons. Okay, so you know that like as you know that these electrons are positively charged and this holes are negatively holes are positively charged and electrons are negatively charged. That is how we consider, right? Holes in the sense like nothing will be there, but generally any place where it can accommodate an electron is said to be a hole. Okay, so since it can take an electron, it is said to be the positively charged. Okay, so just make clear with that. Whenever I am saying that hole is moving, hole will not move. Okay, hole is a place, hole is just a place where it can accommodate the electron. What happens here, holes are considered to be positively charged and electrons are said to be the negatively charged. So here what happens, if you observe, this is negative terminal and this is a positive terminal. So negative is connected to the N side. N side is connected to the negative terminal and P side is connected to the positive terminal. So what happens here, electrons are connected. See, these are also negatively charged and this is also negative terminal. So what happens, both will get repelled, right? Hope you are following. Okay, so what happens here, this electrons will get repelled by this negative terminal. So this electrons will try to move in this direction. Okay, so electrons will move in this direction, and if you observe towards this side also, like this holes are said to be the positively charged, and here I have positive charge and here I have positive charge. Even these holes will tend to repel by this positive terminal. So holes will be moving in this direction. In other way, holes are moving in this direction in the sense holes are moving in this direction in the sense, see, I have electron and hole. Okay, so this is my hole and this is my electron. Okay, hole is moving in this direction in the sense this electron will come and occupy this position, and this will be the hole position. Okay, that's what I mean. Okay. So holes are moving in this direction and electrons are moving in this direction. Okay, but what happens, there is a barrier here. Okay, barrier here in the sense this will not allow the electrons to move from left side to right side. Sorry, right side to left side. Let me just draw it a little bigger for explanation. Here I have positive ions. So what is happening? This negative terminal is repelling this electrons. So what happens? This electron will occupy this position. Okay, in the same way, here the electron will be dragged to this position. Okay, so what will happen? Initially, very small current will flow. Okay, small current, it will be almost negligible to zero. Okay, but once what happens? Once see this now, what will be doing? This VF will start increasing. Okay, maybe 0. Then 0.001, 0.01, 0.02, like that you'll be increasing this. The more you increase, what happens, the movement of this electrons will also increase. Okay, because of that, what happens, this barrier will decrease. This barrier will decrease. What happens, at one particular point, okay, this barrier will completely vanish. There won't be any barrier at that point. Okay, so there won't be any barrier. So see, if there is no barrier, what happens, the electrons can freely move from this n side to p side. Okay, that is what will happen here. Okay, so let me reiterate once again. So initially I have the barrier voltage. Okay, barrier in the sense I will have some negative ions towards this side and I'll have some positive ions towards this side. Now what I'm doing, I'm applying some additional electric field. So because of this electric field, what happens, the electrons which are present in the n side will get repelled by this negative terminal and it will start moving in this direction. And in the same way, the positive terminal is connected to the p side, so the holes will move in this direction. Okay, because of this, what happens, the barrier, the depletion region will start decreasing. Okay, because how it is happening, I'm just telling you. So holes are getting repelled. It means that this will get attracted by this, this will move to this positive ion. Okay, so positive ion, it is moving to positive ion in the sense, like the barrier here, I'll not have any more ions now. Okay, so that is how it happens. Okay, so as I'm increasing this VF, okay, so let me just draw the waveform and show you. If I'm taking VF on x-axis and IF on y-axis. Okay, so what I'm doing, see, if you observe, electrons are moving in this direction because electrons are getting repelled by this negative terminal. Okay, so electrons are moving in this direction. It means that the current flow will be in the opposite direction. Okay, and one more thing, what I'm telling you, see, until the barrier voltage, here I've got the barrier voltage, right? So this barrier voltage, until this barrier voltage is overcome, in the sense until this whatever voltage I'm applying here, this has to be increased more than this barrier voltage. Okay, barrier voltage in the sense that is the voltage required to eliminate this barrier. Okay, so what will happen initially, as I'm increasing the voltage, what happens, the electrons will start getting repelled by the negative terminal and it will start moving towards the junction. Okay, when the electrons are moving towards the junction, this barrier, this depletion region will vanish. Okay, when this exactly will vanish is, for that I have a knee voltage. Okay, so this is said to be the knee voltage. Knee voltage, it is generally denoted as Vk or V gamma. This is said to be knee voltage. knee voltage. So what happens? As I'm increasing the VF, okay, so very small current, very it will be almost negligible current will flow through this. But once this barrier is eliminated completely, what happens? The electrons will become free to move from N side to P side. So the electrons are moving from this side to this side. Okay, so the conventional current direction will be opposite to the electron flow. So that is the reason the current will be flowing in this direction. This is nothing but IF. So what happens, as I've already mentioned, until 0.7 until the knee voltage, very small current will flow, and after that it will increase like this. Okay, so this knee voltage will be 0.7 for your silicon. Generally the semiconductor diodes are made up of silicon or germanium, because even in germanium the outermost shell consists of only 4 electrons. That is the reason germanium and silicon are considered to be the semiconductor materials. To this semiconductor materials will be doping the extrinsic semiconductor trivalent or pentavalent atoms. Okay, so if this PN junction diode is made up of silicon atoms, then the barrier voltage, the new voltage is said to be 0.7. If it is made with germanium, then the barrier voltage is 0.3. So until 0.7 if it is silicon, until 0.7 if it is germanium, until 0.3 there will be very small current flow. After that it will increase like this. Hope this forward characteristics are okay. So here what is happening, the current is increasing, okay, and this type of biasing, when P is connected to positive and N is connected to negative, it is said to be forward biased or forward biasing. Okay, forward biased diode or forward biasing or forward biasing. Okay, so forward biasing, I'm calling this as forward biasing because here I could show you, like after the barrier voltage the current is increasing exponentially. Okay, but what happens when you change the polarity, in the sense negative here and positive here, in that case there won't be any current flow. That is the reason we call it as reverse bias. That I'll teach you tomorrow. Until here, if anybody have doubts, you can ask me. Otherwise, the class is done for the day. It is like until 2:20 only. No, our class is until 2:20, right?
Yes, ma'am.
Okay.
Yes, ma'am.
Yes, ma'am.
Okay. Okay. So if anybody has doubt until here, you can ask me. Okay. Otherwise, you can leave the class now.
Thank you, ma'am.
Thank you. All of you can leave. I'm leaving because I've got a class. Okay, so I'm leaving to the other class. Thank you.